Hello guys, a big thank you for supporting my channel. You have made me very popular and am grateful. Thanks to the students all over the world, especially Pakistan, India, Bangladesh, Rwanda, Zambia to mention but a few. You have been the greatest fans in my teaching career. Thank you for always watching my videos, giving suggestions on, asking questions, making constructive criticism and corrections. I love you so much and wish you success in your academics. Continue sharing the channel with anyone involved with Cambridge Physics. If you are new to my channel, please consider to subscribe and share and like the videos. Hit that like button and bell icon to keep updated. Thank you so much.
Hello, my students. My name is IBM, and I think this is going to be the last lesson of circular motion. This is the last part of circular motion, and I think it's very, very short. It's just further examples and calculated solved past paper. Solved equations or more examples of circular motion. This is lesson 3, and I'm saying this is going to be the last lesson. After this, we shall see simple harmonic motion. So in the other previous parts, we saw concepts of uniform circular motion, including the radian, angular displacement, angular velocity. In lesson 2, we saw centripetal acceleration and centripetal force, and we saw applications of circular motion. And in lesson 3, we just want to finish the last application of circular motion, which is going to be uh, the last part of circular motion, which is going to be the conical pendulum. That is one application of circular motion, which is going to be the conical pendulum. So what do we mean by conical pendulum? Imagine you attach an object on a string and you make it describe a shape which is the shape of a cone. In other words, the object itself is describing a circular path. It is moving in a horizontal circle, but the support or whatever is supporting it is being fixed or is fixed at some point. Say it is attached on a string and is fixed at some point and is made to describe a circular or a horizontal circular path, or it is made to describe a horizontal circle as shown by this diagram here. So let's say that the object moves in a circle whose center is at this point here, and the distance from here up here is the radius of the circle. Of course, the length of the string is this distance here. So this time, the length of the string is not the radius of the circular path, because the string is inclined at an angle, say theta, to the vertical, to make the object describe a horizontal circle, so that the string sweeps through a conical shape. That's why we call it a conical pendulum. So which forces are acting here? One, the weight of the object still exists, so the weight is going to be mg. If the object has a mass m, so the weight is going to be mg. And two, because the object is moving in a circular path, then there is a centripetal force, and because centripetal force acts towards the center, then there is a force which is keeping the object into its circular path, which is directed towards the center, and that is going to be the centripetal force. So the force acting towards the center is equal to the centripetal force that is going to be given by mv squared over r. But of course, as the weight tends to pull away the object, it means there is a tension force in the string which is holding the object, and that tension is going to be T. So if the angle between the vertical and the string is theta, then this is 90 degrees, of course, from the reference point from the center equilibrium position, then automatically this angle is going to be 90 minus theta using the angle sum of a right angle triangle. So automatically this angle here with the vertical is the same as theta. That is, I think those are alternating angles. That is going to be theta. So what remains is just use simple concepts of mathematics, not even physics, or simple concepts of mechanics to come up with the relationships between these forces and the quantities which are given there. So there are only two important forces acting on the particle. We have the tension in the string and the weight of the particle. These ones must be responsible for or must determine what centripetal force we shall be considering in this case. So to begin with, if you use the concepts of AS that you studied, in which unit is that? I think that was force, then stand pressure. If I resolve T in the vertical to be this force here, which would be T sine, actually because I'm using theta, it would be T cos theta. And for equilibrium in the vertical, I will say that T cos of theta is going to be equal to mg. And if I consider T in the horizontal, it is going to be T sine of theta. When I resolve T in the horizontal, if I use the angle cos, the angle theta, so it is going to be T sine theta, or T cos of 90 minus theta, which is the same as T sine theta, is going to be equal to the centripetal force, which is mv squared over r. So that means if I divide the two equations, equation 2 might divide by equation 1, I have that T sine of theta divided by T cos of theta is going to be mv squared over r divided by mg. So this means tan of theta is going to be equal to v squared over r times g. So it means the relationship between the angle between the vertical, the linear speed, and the radius of the circular path is tan theta is equal to v squared over r. Of course, you don't need to cram this expression here. If you have some basics of maths, if you have some basics of mathematics, you can always derive these expressions. So the remaining expressions that you may need in this case could be for trigonometry, or you could also recall using V equals to omega r. You should also recall using omega equals 2 pi over t where necessary. You could also recall using centripetal acceleration is v squared over r where necessary, and so on and so forth. The rest would be concepts of trigonometry, opposite, sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent where necessary. So that one is an application. This is the object describes a conical shape. It makes the string to sweep through a conical shape whose angle is theta from the vertical. So that's why we call it a conical pendulum. Okay, so we have done the resolving, and we have seen what t sine theta equals to. We have seen t cos theta equals to mg, and we have combined the two expressions to come up with the fact that tan of theta is equal to v squared over r. Of course, like I said, you don't need to cram this expression. You can always derive it from simple concepts of AS physics, that involves resolving. So I think that is the conical pendulum. The only thing which remains now is doing examples or further examples about circular motion. So a mass of 0.2 kilograms is whirled in a horizontal circle of radius 0.5 meters by a string inclined at 30 degrees to the vertical. Find the tension in the string, find the tension in the string, find the speed of the mass on the horizontal surface, the length of the string, the angular speed. Okay. So I'm going to just sketch something here for simpler reference. So let this be the reference point, the vertical. It is wired in a horizontal circle, but the string is inclined at 30 degrees to the vertical. So this is going to be the string. Let the object be here, and it is describing a circular path like this one here. But I'll just sketch part of it. This is the center of the circular path. So this is going to be the radius. This is going to be the length. So the angle from the vertical is 30 degrees. You can draw a complete conical path for the object. So the mass is 20 kilograms. So that means the force acting vertically downwards is going to be, sorry, the mass is 0.2. So the force acting down is 0.2 times g, where g is acceleration due to gravity. Let me change the color to green. So it means there is tension in the string, and we can resolve the tension vertically upwards. The tension is going to be T, because the other angle to the vertical is 30. This angle is also 30. So the tension is going to be T cos of 30 degrees. Then the component of the tension which acts towards the center is the one which provides centripetal force, and this component is T sine of 30. So part 1 tells us to find the tension. So we have that T cos of 30 is equal to mg. That is AS physics. So this means, or this implies, that the tension is going to be mg, where mg is going to be 0.2 times g, which is 9.81, divided by cos of 30. So 0.2 times 9.81 divided by cos of 30. So this is 2.27 or 2.3 newtons to two significant figures. Then that's Roman 1. Roman 2, the speed of the mass on the horizontal surface. The speed of the mass on the horizontal surface. So we want to find the speed. So we have that the horizontal component provides centripetal force. So we shall simply say that m v squared over r, which is the centripetal force. Remember, I'm attempting part 2. mv squared over r is equal to t sine of 30. So I have the radius. I think they've given us the radius of the horizontal circle as being 0.5. T, we have already got it as approximately 2.3. So I want to find V. So V is going to be T, which is 2.3, sine of 30, times R, which is 0.5, then divide by the mass. So divide by the mass, which mass is 0.2. Then this should be under the square root. So I'll use 2.3 because I rounded off. 2.3 sine of 30, then times 0.5, divide by 0.2 under the square root. So this is giving me 1.7, approximately 1.7 meters per second. So that is the speed. Then the length of the string, so we want to find L. So that is just entirely trigonometry. You consider this triangle here. This is L. This is 90 degrees. This is 30. Of course, this angle is not known, but we can calculate it. This is R, which R is 0.5. So you have opposite is 0.5 and hypotenuse is L. So that is sine. So sine of 30 is equal to the opposite 0.5 over the hypotenuse, which is L. So L is 0.5 divided by sine of 30. Of course, sine of 30 is 0.5. So here the answer is going to be 1.0 meters. So the length of the string is 1.0 meters. Then the angular velocity, so this was part 3. The angular velocity, that is going to be part 4. The angular velocity is omega, which is going to be v divided by r, and v is 1.7 approximately, divided by the radius, which radius is 0.5. So 1 divided by 1.7 divided by 0.5, this is twice of that, which is 3.4. So the angular velocity is going to be 3.4 approximately meters per second. So because I rounded off these values, that's why you see my angular velocity. Actually, this is radians, not meters per second. It's radians per second. The angular velocity should be in radians per second. So depending on what value, how you rounded off these values, you may get very close to these answers. But I know that this is correct. It's always the examiner who determines the tolerance that should be accepted in that particular case. Okay, let's see example number 2. A mass of 0.2 kilograms is whirled on a horizontal circle of radius 0.5 meters by a string inclined at 30 degrees to the vertical. Calculate the speed of the mass in the horizontal circle. I think this is almost the same thing apart from okay, so we want to find the speed of the mass. They have given us the mass, they've given us the radius, and they've given us the angle of inclination. So I would first sketch here. This is the vertical reference form, and let's say the mass is somewhere here, describing a horizontal circle, because it's inclined at an angle of 30 degrees to the vertical. So let this be the horizontal distance, which is the radius of the circular path, which is 0.5. So the forces acting, there is tension downwards, which is going to be 0.2 times g. That is the weight down. Then there is tension upwards, which I'll call T. So this is T. We resolve using this angle of 30 degrees. So this is going to be T cos of 30. Okay. So we want to find the speed of the mass. The expression which has the speed is in the horizontal. So I'll start with the horizontal. Remember, the component of T in the horizontal provides the centripetal force. And the component of T in the horizontal is going to be T sine of 30. But since I don't have T, then it means I will need to consider both vertical and horizontal to find T. So considering vertical motion, vertical, we have T cos of 30 being equal to mg, which is 0.2 times 9.81. Then considering the horizontal, I have that T sine of 30 equals to centripetal force, which is mv squared over r. So the component in the horizontal points towards the center, therefore provides centripetal force. Remember, I want to find v, so I'm going to divide equation 2 by equation 1, which gives me tan of 30. So tan of 30 is going to be equal to v squared. Of course, the mass cancels out. This is m, so m cancels out. This is the same as 0.2 times v squared over r. So 0.2 cancels out when I divide this equation by the other one. So I remain with the v squared over r times g, which is 9.81. So I make v the subject, so it means v is going to be the square root of r, which radius is 0.5, times g, which is 9.81, then tan of 30. So I'll just press my calculator. So 0.5 times 9.81 tan of 30 square root. So this is still 1.7 meters per second. So the speed is 1.7 meters per second. Then calculate the length of the string. So we have opposite hypotenuse. If we look at that triangle, we have a triangle like this one here, where this angle is 30 degrees. This is L, this is 0.5. So that is sine. Sine of 30 is equal to the opposite, which is 0.5 divided by L. We have already seen that L is going to be 0.5 divided by sine of 30, which is equal to 1.0 meters. Then the vertical height. We want to find the vertical height, h. This is h. We want to find the vertical height h. That is still trigonometry. The vertical height from the point of suspension to the center of the circle. So you can still use trigonometry, maybe opposite, adjacent, that is cos. So I would say cos of 30 equals to the opposite, which is 0.5 um, over the adjacent, which is h. So this means h is going to be 0.5 divided by cos of 30. So 0.5 divided by cos 30. So this is approximately 0.58. So that is the vertical height from the point of suspension to the center of the circle. Then the angular speed, so omega is equal to V over R, which is simply going to be 1.7 divided by R, which R is 0.5. We have already seen this is going to be 3.4. That is 3.4 radians per second. Then the period. We know that period is going to be, because we know that omega is 2 pi over t, then t is going to be 2 pi over omega. So when we substitute, this is going to be 2 pi divided by omega, which omega is approximately 3.4. So I'll just press my calculator. 2 pi divided by 3.4. So this is 1.85. Approximately 1.85 seconds. So that will be the period. Okay, so we have just played around with expressions. So that is not really something very, very big. We just play around with those expressions, those equations, and we arrive at the answers which are required by the examiner. Okay, more examples. So these are going to be further general examples. The planet Mercury takes 88 days to orbit once around the sun. So this is the period, capital T. Calculate its angular displacement in radians at time intervals of 44 days, 1 day. So 88 days corresponds to one revolution. Remember, one revolution or one orbit. One orbit is one complete cycle. And this is equal to 2 pi in radians. That is, one cycle is 2 pi in radians. That is one orbit. And the time for one orbit is 2 pi radians. So we want to calculate the angular displacement, that is delta theta, in radians. Remember, delta theta is the ratio of the arc length, delta S, the ratio of the arc length to the radius of the circular path. That is the angular displacement. The ratio of the arc length to the radius, that is the angular displacement. And the arc length for one cycle it is 2 pi radians. So if arc length is 1 cycle, then that is 2 pi radians. Then calculate its angular displacement in radians during a time interval of 44 days. So there are several ways of doing this. You can use, period is equal to 2 pi over omega. Period is 2 pi over omega, where omega is angular velocity. So period is 2 pi over angular velocity, and also angular velocity, omega, is the rate of change of angular displacement, which will be delta theta divided by delta t. Okay, so we can look at these two expressions. Let me just combine these two for simplicity. So it means the period t is the same as 2 pi divided by, where there is omega, I have delta theta divided by delta t. So delta t goes up. So this is going to be times delta t. So since they have given us the values of t, of small letter t, that is the time, so it means delta t is going to be equal to, I'm making delta t the subject, so it is going to be equal to delta theta divided by 2 pi times the period, capital T. Is that correct mathematics? No, we want to find angular displacement, so I have to make delta theta the subject, not t. So I'm making delta theta the subject. I will not use this. I'm making delta theta the subject, so delta theta is going to be equal to 2 pi over t times the time t. So, it is delta t over t times 2 pi. So I'll just substitute for the first one, a. So for a, this is going to be, delta theta is going to be equal to t, which is 44, divided by capital T, which is 88, then times 2 pi. So this is going to be equal to, I think that is going to be pi. This is just pi. It is a half times 2 pi, which is pi radians, or 3.14. Then the second one, delta theta, is going to be equal to 1 day divided by 88 times 2 pi, which is 1 divided by 88 times 2. So this is 0.071. Yes, 0.071 in radians. Since they wanted the answer in radians, so the answer is going to be that, and this one here. Okay, so I combined these two expressions and I was able to come up with what is necessary. In each case below, state what provides the centripetal force on the object. A car travels at a high speed around a sharp cone. Of course, if it is traveling around a sharp cone, it is the friction. Friction between the ground, or between the road and the wheels. So that one is responsible for centripetal force. A planet orbits the sun. Of course, this is the gravitational pull. Gravitational pull between the sun and the planet. An electron orbits the positive nucleus of an atom. Of course, if it is an electron, the force is electrostatic. So this is electrostatic force. Electrostatic force. That is the electrostatic force between the positively charged nucleus and the electron. Then clothes spin round in the drum of a washing machine. So this is, I think this is the contact force, which is the normal reaction. Contact force between the clothes and the surface of the drum. Okay, so I think I gave here the answers. Friction between the tires and the rod. Then I also gave gravitational force between the planet and the sun, or on the planet due to the sun. Electric force, which is the electrostatic force acting on the electron due to the positive charged nucleus, that is the electrostatic force. Then we have the contact force, or the inward contact force between the clothes and the rotating drum. There is that contact force at the point where the clothes touch on the surface of the contact drum. So those ones are responsible for providing the centripetal force. An aeroplane is circling in the sky at a speed of 150 meters per second. The aeroplane describes a circle of radius 20 kilometers. For a passenger of mass 80 kilograms inside this aeroplane, calculate her angular velocity, her centripetal acceleration, and the centripetal force. So I'll start with part A. Angular velocity, so we know that omega is equal to v over r, which is going to be equal to 150 divided by r, which is 20,000. So I'll just press my calculator. So this is 7.5 times 10 to the power of 5 radians per second. I'll check it again. 150 divided by 20,000. It's 7.5 times 10 to the power of minus 3. That is power minus 3. Because it was 20 kilometers. Okay, I think that is correct. Then part B, centripetal force, centripetal acceleration. So the centripetal acceleration is equal to v squared over r, which is the same as omega squared times r. So this is going to be omega is 7.5 times 10 to the power of minus 3. This is minus 3. Then this should be squared. Then times the radius, which is 20,000. So that should be squared times 20,000. So this is giving me 1.125 meters per second squared, or approximately 1.1 meters per second squared. Then part C are the centripetal force acting on her. So we know that centripetal force is mass times centripetal acceleration. Since I already have the centripetal acceleration, I don't want to waste time. I'll just simply say the mass is 80 times the centripetal acceleration, which is 1.1, or which is 1.125. So times 80. If I say 80 times 1.1, it is either 88 or approximately 90 newtons to one significant figure. Okay, it is supposed to be, I think, approximately 88. If I use 1.1, it will be 88, but rounds off to the same thing. If I use exactly 1.125, it will be 90. Okay. Yeah, I think those answers are correct. The diagram shows a stone tied to the end of the length of a string. It is whirled around in a horizontal circle of radius 80 centimeters. The stone has a mass of 90 grams and it completes 10 revolutions in a time of 8.2 seconds. So that means we can find the period. It makes 10 revolutions in 8.2 seconds. So the period is going to be the number of revolution, the time, total time, which is 8.2 divided by 10 to find the time for one revolution. So this means this is going to be 0.82 seconds. So that is the period. Then calculate the distance traveled by the stone. The distance traveled by the stone during one revolution. This is the distance. This distance is equal to the circumference of the circle. So if it is equal to the circumference of the circle, then we shall just substitute it here. The distance for one revolution is 2 pi times r, which is going to be 2 pi, and the radius is 80. 80 times 10 to the power of minus 2. I think this is automatically, let me press my calculator, 2 pi times 80 exponent minus 2. So this is 5.03 meters. So that is the distance. Okay, I think example 4 is still continuing. Then the speed of the stone as it travels in the circle. Speed of the stone as it travels in the circle. I'll do that one here. Okay, I'll do it in the next page. Speed of the stone as it travels in the circle. So we want speed is going to be omega times r. And omega is 2 pi divided by t. Then we multiply this by r. So we have the period and we have the radius as 80 exponent minus 2 or 0.8. So I'll just do that here. So the speed v, that is Roman 3. V is equal to omega times r, which is equal to 2 pi over t times r. So v is going to be 2 pi. The period was the time for one revolution, which is 0.82. The radius is 80 centimeters, which is 0.8. So I'll just press my calculator. 2 pi times 0.8 divided by 0.82. So this is giving me 6.13 meters per second. Okay, then Roman 2, they are saying the centripetal acceleration. So I'll do Roman 2 here. Not Roman 2, Roman 4. This was Roman 3. Roman 4 is the centripetal acceleration s, which is v squared divided by r. So which will be 6.13 squared divided by a radius, which was 0.8. So let's see, the centripetal acceleration is 6.13 squared divided by 0.8. Normally, when you are finding an answer which is which you are sure you may use in the next part, it's better you have at least 3 significant figures. So this is going to be 6.97, or approximate, I'll just write 47 meters per second squared. Okay. Then part 5, the centripetal force. Of course, centripetal force is equal to the mass times the centripetal acceleration. I think the mass was, what was the mass? The mass was 90 grams, I think. The mass is 90 grams. So it is going to be 90 times 10 to the power of minus 3, then times the centripetal acceleration, which is approximately 46.97. So I'll say 46.97 times 90 exponent minus 3. So this is giving me 4.23 newtons as the centripetal force. Then what is the, so this was part B. Then part C, what is the angle between the acceleration of the stone and its velocity? So this one does not require calculation. No, this was part 5. Part B is what provides the centripetal force on the stone. Remember, it was attached on the string, so it is the tension. Tension in the string. Then part C, what is the angle between the acceleration of the stone and its velocity? Of course, this is without calculation. It is always 90 degrees. If you recall, for any object moving in a circle, for any object moving in a circular path, the velocity is always perpendicular to the radius. So this is velocity, and remember the force is always acting towards the center. The acceleration is also acting towards the center, so the velocity is always perpendicular. Uh, the velocity is always perpendicular to the acceleration. So because the stone describes a circle, therefore the angle between the velocity and the acceleration must be 90 degrees. So 90 degrees because um, because the stone describes a circle. If an object describes a circle, then the centripetal force is in the same direction as the acceleration, centripetal acceleration. The velocity is always perpendicular to the centripetal force and is also perpendicular to the centripetal acceleration. So the angle is 90 degrees. Okay. Yeah, so the answers were given here, but I've already solved them. Even if I've already solved them, the stone describes circle, therefore the angle between the velocity and the acceleration must be 90 degrees. So that one has already been solved. A lump of clay of mass 300 grams is placed close to the edge of a spinning turntable. At the center of mass of the lump of clay travels in a circle of radius 12 centimeters. The lump of clay takes 1.6 seconds. Sorry about this. The lump of clay takes 1.6 seconds to complete one revolution. So this is the period. Time for one revolution. Calculate the rotational speed of the clay. So we want to calculate the rotational speed of the clay. The center of mass of the lump of clay travels in a circle of radius. So this is R, 12. It's 12 centimeters. A lump of clay of mass 300 grams. So we want to calculate the rotational speed of the clay. So we can simply say speed is equal to distance over time. Because we have the time for one revolution, so we can say the distance is going for one complete cycle is the circumference, which is 2 pi times r over the time, which is the period. So this is going, or you can use omega times r, where omega is 2 pi over t. So this is going to be equal to 2 pi times r, which is 12 centimeters, I think is 0.12. Then the period is 1.6. So I'll just press my calculator. So 2 pi times 0.12 divided by 1.6. So this is 0.47 meters per second. Then calculate the frictional force between the clay and the turntable. So we want the frictional force. Remember, it is the frictional force which is going to provide the centripetal force. So the frictional force will be the one to provide centripetal force. So this is going to simply be equal to mv squared over r, which is going to be the mass is 300 grams, which is I think 0.3 kilograms, times v, which is 0.47 but squared, divide by the, of course, the distance from the stone to the center is going to be the radius, which is 0.12. So 0.3 times 0.47 squared divided by 0.12. So this is giving me a 0.55. So I'm saying the centripetal force, the friction between the clay and the surface is the one which provides centripetal force, so they are going to be equal. I'm saying the friction in this case is going to be equal to the centripetal force. Okay, I think it is still continuing. The maximum magnitude of the frictional force F between the clay and the turntable is 70% of the weight of the clay. So the maximum magnitude of friction is 70% of the weight of the clay. What does that mean? So we can say friction is 70% of mg. So the speed of rotation of clay is slowly increased. So the speed of rotation of the clay is slowly increased. Determine the speed. So this is not parts, it is just a continuation. Determine the speed of the clay when it just starts to slip off the turntable. So the frictional force is 0.7 because 70% is 0.7, so it is 0.7 of mg. And remember the friction was equal to the centripetal force, so I will simply say 0.7 mg is equal to the centripetal force, which is mv squared divided by r. I don't need the m here. So I will make v the subject, and v is going to be equal to the square root of 0.7 times r. So I'll just substitute here, or there is a g here, times g. So which will be the square root of 0.7 times the radius. I think the radius was 12 centimeters, so it is going to be 0.12 times g, which is 9.81. So 0.7 times 0.12 times 9.81 under the square root. So this is 0.908 or 0.91. So the speed is going to be 0.91 meters per second. The question said when it just starts to slip. Of course, when it just starts to slip, which is when the frictional force is just equal to the centripetal force. If it is already slipping, it is because the frictional force is now less. It cannot be equal to the centripetal force. But if it just starts to slip, the frictional force is automatically equal to the centripetal force. Okay. Yeah, I think the answers are correct that we have just done. Example number 6. The diagram shows a skateboarder of mass 70 kilograms who drops through a vertical height of 5.2 meters. So it drops through a vertical height of 5.2 meters. This is 5.2 meters. Okay. I think it continues to the next slide. We should just first of all look at the radius of the curvature. The distance from the center of curvature is 16 meters. So of course at this point we expect that he has a gravitational potential energy, which is mgh. And it's this gravitational potential energy which is going to be lost as gains kinetic energy. Okay, let's see what the question tells us. The The deep has a radius of curvature of 16 meters. Assume no energy losses due to air resistance or friction. Capture the speed of the skateboard at the bottom of the deep at point B. Of course, at point B, where is at the bottom, we expect the speed to be maximum. You may assume that the speed of the skateboard at point A is 0. That is, we can just use conservation of energy. So using conservation of energy, then it is going to mean that the loss in gravitational potential energy is equal to the gain in kinetic energy. So I'll use this space here because I don't have enough space. Let me use this space here. So I'll say kinetic energy at B is equal to the loss of gravitational potential energy from A to B. So because at B was at a higher level and there is no friction, there is no air resistance, so the kinetic energy at B is equal to the loss in the gravitational potential energy from A to B. So kinetic energy is going to be a half m v squared, and the loss in gravitational potential energy, because at A the speed was 0, so the energy there was 0, but the potential was equal to mgh. So this is going to be equal to mgh. If B is the reference point where h is 0, so the potential at B is going to be 0. If we cancel out m, it implies that we want to find the speed. So V is going to be equal to the square root of 2gh, to be 2gh. So I'll just substitute in this to be the square root of 2 times 9.81 times h. I think the vertical height was 5.2? Yes, 5.2 meters. So this will be times 5.2 meters. So what is this speed? So 2 times 9.81 times 5.2 under the square root. So this is 10.1 meters per second. So that is the speed. So that is the speed of the skater at the bottom. Then part B is saying calculate the centripetal acceleration of the skater at point B. So if I want to find centripetal acceleration is going to be v squared over r, which is going to be 10.1 squared. The radius was 16 meters, so it is over 16. So 10.1 squared divided by 16. So this is 6.38, which is 6.4. So this is 6.4 meters per second squared. Calculate the contact force R acting on the skateboard at point B. So if I consider the diagram here, when it's just at B, at point B, the contact force acts vertically upwards, and it's going to be equal to and of course there's a normal reaction force which is acting upwards. So the resultant force here, remember, is equal to the resultant force at any point is going to be the centripetal force. So the resultant force, net force, is given by the mass times acceleration, which acceleration is the centripetal acceleration. So then the resultant force, which is mass, times the centripetal acceleration, is going to be equal to the difference between those two values. If the resultant force points towards the center, then this is going to be equal to R minus mg. So R is the contact force, then minus mg, that is going to give us the resultant force. So it means the contact force R is going to be the centripetal force, or the resultant force, which is ma plus mg. So this is going to be m into a plus g. So I can just simplify this. What is m? The mass was, I think, 70. The mass of the child was 70. Okay. So this is going to be 70 into A, which is the centripetal acceleration, which is 6.4, plus G, which is 9.81. I want to use 6.38 so that I have three significant figures for both. This was 6.38 plus that. So I'll just press my calculator. So 6.38 plus 9.81 times 70. So this is giving me 1,133. 1,133 newtons, or approximately it is 1,100. So R can be written as 1,100 newtons to two significant figures. Okay, so I think that is fine. Yeah, the answers are given there. I think they are correct. Then examples are being continued here. A car of mass 820 kilograms travels at a constant speed of 32 meters per second. So this is V. This is M. Along a banked track. So banking is like raising a track above an angle to the horizontal. The track is banked at an angle of 20 degrees. The net vertical force on the car is 0. The net vertical force on the car is 0. The net vertical force on the car is 0. What does that mean? When I resolve R to the vertical, it should be equal to the weight so that the net vertical force is 0. So if this angle is 20 degrees, let me take this further. This is going to be 90, 20. This angle is going to be 90 minus 20, I think. So if this is 90 minus 20, this is going to be 20 because the whole of this angle here is still going to be 90. So this is going to be 20, which means this angle is also going to be 20 degrees. So it means if I resolve R to the vertical, it is going to be R cos of 20 degrees, and it should be equal to the weight downwards because they said the net vertical force on the car is 0. Use this to show that the contact force R on the car is 8.56 newtons. Okay, so in part A, I will have that R cos of 20 is going to be equal to the weight, which is equal to mg, which is going to be mg. So it means R is going to be the mass, which is 820, times g, which is 9.81, divided by cos of 20. So I'll press my calculator. So 820 times 9.81 divided by cos of 20. So this is giving me 8,560 newtons, which is of course 8.56. 1, 2, 3 kilonewtons. Then part B, use the answer from A to calculate the radius of the circle described by the curve. So in part B, we are going to find the radius. So since we have R, the component of R, or the force which points towards the center, is the one which provides centripetal force. So I have to resolve R in the horizontal. So I'll say R sine. The component of R in the horizontal is going to be R sine of 20. So R sine of 20, why am I repeating myself? R sine of 20 is going to be equal to the centripetal force, which is mv squared divided by R. So the component, the force which points towards the center, is the one which provides the centripetal force. So it means the radius r is going to be the mass, which is mv squared divided by r sine of 20. So this is going to be mv squared, which is 820, times v squared, which is 32 squared, divided by r, which r is 8560, times sine of 20. So I'll just press my calculator. 820 times 32 squared divided by 8560 sine of 20. So this is giving me 287. So r is about 287. Small r is about 287 meters, or you can write approximately 290 meters. Yeah, so those are the answers we expect. Then a stone of mass 120 grams is fixed to one end of a light rigid rod. The stone is whirled at a constant speed of 4.0 meters per second in a vertical circle of radius 80 centimeters. Calculate the ratio tension in the rod at A divided by tension in the rod at B. So we have tension in the rod at A over tension in the rod at B. Okay. So we can call tension in the rod at A T1, and tension in the rod at B we shall call T2. So of course we know that I'll call this TA. I'll call this one TB. So TA, of course, there is a weight here which acts downwards. This is mg. And there is also a force here which acts downwards, which is mg. So if I just come up with a diagram, for clarity, at B, the tension is acting towards the center, and then there's weight mg. Then at A, the tension is acting towards the center. Then, of course, tension always acts away from the object. So we shall have that T at, say, A is going to be equal to, no, let me just say the resultant force, which is going to be the centripetal force at A, is going to be equal to TA minus mg. That is the resultant force at A. It is TA minus mg. So remember, this is centripetal force, so it is going to be mv squared divided by r, where r is the radius. So this means that TA is going to be mv squared over r plus mg. At the same time, or you can substitute if you want. M is 120 grams, I think that is 0.12. 120 divided by 1,000, that is 0.12 times V, which is 4 squared, divided by R, which is 0.8, plus 0.12 times 9.81. So what is TA? So TA is 0.12 times 4 squared divided by 0.8 plus 0.12 times 9.81. So this is giving me 3.6 newtons. Then at B, so the resultant force, which is the centripetal force at B, is going to be equal to, because TB and mg are acting in the same direction, so it means the centripetal force, it means that TB is equal to the centripetal force, which is mv squared over r minus mg. So I'll just substitute. TB is going to be equal to 0.12 times 4 squared divided by 0.8 minus 0.12 times 9.81. 0.12 times 4 squared divided by 0.8 minus 0.12 times 9.81. So this is giving me 1.2. So TB is going to be equal to 1.2 newtons. So we want the ratio. So the ratio TA divided by TB is going to be 3.6 divided by 1.2. So 3.6 divided by 1.2, that is equal to 3. So this is 3.0. So that is going to be the ratio. Yeah, I think you deserve to do some questions for yourselves. You deserve to do some self-check questions for yourselves. An astronaut, as part of her training, is spun in a horizontal circle of radius 5 meters. If she can withstand a maximum acceleration of 78.4 meters per second, what is the maximum angular velocity, that is omega? So this is centripetal acceleration, this is radius. What is the maximum angular velocity at which the astronaut can remain conscious? And I've given you the answer here, you can just verify that. A particle of mass 0.2 kilograms is attached to one end of a lightning extensible string of length 50 centimeters. The particle moves in a horizontal circle with an angular velocity of 5.0 radians per second, with the string inclined at an angle theta to the vertical. Find the value of theta. So if you sketch this, this is the vertical, then the string is here, the particle is just there, describes a horizontal circle. This angle is theta, and this length has been given as 50 centimeters. So this is the radius, which is not known. So you have to find omega and try to verify and see if the angle is 30 degrees. We have done several examples for that. Okay. Then self-check question number 3, I think. A particle of mass 25 kilograms, 0.25 kilograms, attached to one end of a tight, inextensible string of length 3 meters. The particle moves in a horizontal circle. The string sweeps out the surface of a cone. So if you sketch this, this is the vertical, this is going to be the position of the object. So it describes a cone. Okay, so the length of the string is this distance here, which is 3 meters. The particle moves in the horizontal circle and the string sweeps out the surface of a cone. The maximum tension that the string can sustain is 12 newtons. So there is tension, of course, in the string. The tension T in the string is 12 newtons. Find the maximum angular velocity of the particle. So you should be able to verify that the answer is that, because I have done an example, or I've done a few examples for that. So you should be able to, this is going to be the radius. You should be able to get to find the maximum angular velocity as that. I think that is the end.